Okay, so far we discussed some applications of the integrals, and mostly what we really emphasize here is how do you formulate the problems, how you formulate the integrals. So it won't just you don't have to memorize formulas. Just what you need to do is to understand is how to make the formulas instead of using formulas. Okay, instead of memorizing formulas. Okay, so what we have done is we have done area. Although we will do some more problems on this type of this kind of exercise. We do compute some volumes of a solid which obtain from revolutions. So revolving an area around certain axis, and you get a solid. How to compute it, and this parallel cutting thing. Okay. So we'll do some more problems of this later on in the tutorial sessions. So let's continue with other example applications. Okay, we skipped a left an area, surface area. We skipped that one. So we'll continue with a sorry, which one is okay here. So need to explain a little bit of physics of a mechanics that you probably covered that in the first 3 or 4 weeks of the semester, September or something. That's about a moment and center of mass. So we're computing center of mass of an object called lamina. Okay, so let's we call a moment. Moment basically is a distance times a mass. Mass times distance. Basically, that's the thing that we need to know. Okay, so let's do this one, for example. If you have a, say, a mass distributed over a segment of lines. Okay. Yes, this is mass. On line, discrete mass. So means points mass. Not necessarily homogeneous in the distributions. Okay, say this is has a x1, x2, x3, dot, 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 dot. This is x and minus one x. M. So m mass actually. Right. So let's this is a, say, x bar. What is x bar? So moment with respect to width. So WRT, that is with respect to, right? So moment of this mass respect to this is the sum of let's see, this one here, sum of to n I times the difference. So xi minus x bar. Okay, so this is moment with respect to, to this x bar. What does it mean here? So if that's in stable conditions, equilibrium, yeah, stable. So that means this moment is zero. Okay, so if you plugged it in, what does it mean? Moment is zero. So that means this one. So sigma mi x 0. And if you that means so just m times xi equals to m times x bar. Okay, so this bar means just like an average, so that if you compute this, what you get here is x bar is actually just okay. Oh, sigma, forget. This is m, sorry, yeah, this is also mi. Okay. Now that because x bar is constant, so this looks like this ball. Okay, so this is a total mass. Okay. So we can compute now the x bar is actually let's see, x bar is actually this one, total moment over this one, total mass. Okay. Total mass. Okay. So in this case, this x bar is called the center of mass. Okay. So now you get center of mass a formula. Right? Questions? So in this case, what we have is that you have m mass here, m masses, right? But from afar, it looks like only one mass. That one mass is the center. Okay, so the whole m masses here is represented by a point. So this is interpretations. That m masses is represented by one mass position at x bar. Okay, so that's what we call center of mass. So it's like a when you think about the picture of a galaxy. sample. Okay, so just bunch of stars, nebulas, all those stuff. Okay, and from afar it looks like a just a point. Okay, so it's from afar it's like a point mass. Okay, so point mass. What's the point mass? The mass is the total of the that galaxy, and the coordinate is that center of the galaxy. Okay, so that's the total mass. Okay, so let's just do directly to what has to do with the integrations. Okay, let's jump to the two dimensions. Uh, what we call lamina is a two-dimensional object. Uh, thin. Almost has no thickness. Very thin. Thickness very thin. Small thickness. Okay, so it's almost like a plane. Okay, and all right. So what our objective is find center of mass. That is x bar, y bar. Okay, so that's our objective. Okay. Okay, let's do this one here. Uh, suppose we are going to find the thing. Okay, so this is laminar, bounded by x, x-axis, x equals a and x equals b. So this is so we assume that the lamina is homogeneous with respect to y. Respect to okay, so that means if you think about the mass density over here, for example, there's the same mass density as this, as here, as here. It might be different, but along this line, mass density is the same. That means homogeneous means mass density on the line x equals something. Uniform. So only depends on x. So the thing is, because we just do one variables, not two. Okay. If we use dependence on y also, then we have two variables, function of two variables, x and y. At least at this point, we don't want to do that. Next semester we'll do that. Okay. Okay, so let's compute the. Our objective is to compute the center of mass. Okay, so this is the our object. We're going to find the center of mass. Okay. Okay, so we assume that this function has a homogeneous everything. At least for a moment. Homogeneous lamina, everything. So the density does not depend on x and y. Density is independent of x, y. All right, so let's compute the moment. Okay, what moment? Let's see. Just erase this one. Let's see. Okay, just take one as usual. We chop this out, make a partition. Okay, and take one sample. This is a sample. So this is xi minus 1, xi of length delta x. The height is, see, this is f of x. So let's see. We compute the moment with respect to y-axis. Okay. So this distance here. So you got to multiply with this distance. Respect to y-axis. This distance is the x coordinate. Okay, so this distance here, the x coordinate. So this moment here is delta m y. Okay, so this is just a, what do you call it? X times mass of this. Okay, and so say the density is just delta. Density. So it's just delta times the area of this. Okay, so mass is delta times area, density times area. Density times area. Density is, no, so the area is just delta x times f of x. Okay, so what you have is delta x f of x, delta x. So this is at I. Okay, so the total moment on with respect to y-axis of lamina is so the my, so it's not the delta, is just the, say, can be approximated by this sum. Okay, so delta x I f x I. Okay. And so this is a Riemann sum. Okay, so this take limit as usual. So this moment is actually limit of Riemann sum. That is the integral of delta x f of x dx from, say, in our example, from A to B. Okay, so that's what we call my, the moment. Okay, while we know the total mass is just, well, delta, because delta is a uniform, the density uniform is just same as area. Okay, so mass times area, sorry, mass times density. Mass is area times density. Okay, so this is total mass. So now we have that the x bar is actually there. Okay. So if you write this in term of integral, you would have this formula here. You take delta out, right? It's just x f of x dx. And the mass is, so in this case, delta cancel, right? So it just this integral x f of x divided by this area here, integral f of x dx. Okay, so that's the x coordinate. What about the y coordinate? So the question is y coordinate. Okay. All right, so let's look again at our sample. This is delta x I x minus 1 xi. All right. Okay, so we're computing. So let's see. We're computing the moment with respect to x-axis. Moment with respect to x-axis. Moment with respect to x-axis, that is the, so this is the x-axis, say. Okay. The thing is, what is the distance with the x-axis? For here, there's 0. Here, something, there's something, something. All different. So you might think, what happened? How we compute the mass? Okay. And because this is a rectangle, so just replace this rectangle by a point mass, which is the center. Okay. So this is, replace this sample mass by its mass. So what's this? That's in the middle, exactly in the middle. So what's this coordinate? The coordinate is the average of this one. So x that's the x, and y is also the f of this point. That's the coordinate of the center. Okay. But we for small delta x, we see that xi minus 1 is almost the same as xi, right? Okay, so center of mass is above of sample. Is you say, okay, so xi, okay, let's see, and so if this is 1/2, okay, sorry, this is supposedly 1/2. Okay, so if you replace this by point mass, this is the location of point mass. So the moment respect to x-axis is that that is the, we call it, so mass times distance times distance, which distance? This distance here. It's approximately. Okay, so the total moment with respect to x-axis is this side. So in this case, what is mx? Mx, the limit of this, which is, and take limit, which becomes integral a to b. So this is mass is the density times area. Sorry, how to find this one? Height is f of x, and this is delta x. Delta. Okay, so what we have is 1/2 delta over 2, right? So this is 1/2 x. Okay, so this is the x. So then we have this 4 is the x over m, which gave you delta over 2 this is delta times 1/2 of that. Okay, so basically you have three integrals. Okay, questions so far? Let's do some example. One example, just pick one problem. Let's do this one, all right? Center of mass equals centroid. Okay, you consider a region bounded by the curve x cubed and square root of x. Okay, we need to find the centroid. Well, it's not, uh, let's find something. Let's see, something more symmetric. Okay, just all right, so this one is problem 9. Okay. So, a centroid bounded by 2 minus x squared and y-axis. Y equals 0. All right. Two, like this. Yeah. Okay. So this is 2. If y equals 0, then square root of 2. Okay, so y equals 2 minus x squared. Okay, so this lamina is here. Okay. So suppose mass density is, the density is delta. Right. Okay, because this is metric, by symmetry, we know the x bar should be here. So then we don't have to compute x bar. We just need to compute y bar. Okay. So the y bar, how to get the y bar? Well, think about one sample. So y bar to find y bar, we need uh, to compute moment with respect to x-axis. With respect to x-axis. Okay. So this is the sample. This is the center of mass, the centroid of this sample. This is of approximately with a xi and 1/2 of xi. So this is the center of mass. So for this moment, for this one is let's see, mass of this is delta times mass distance. Okay, mass first, delta times area. Area is area times distance. Distance is just 1/2 of. Okay, so then that's the moment of the sample. So this moment respect to x is just the sum. Okay, let's write this down and take delta out because there's a constant. All right, so this is, oh, you can take 1/2 out also, so it's delta over 2. The sigma, this is 1/2 square times delta x. In this case would be, what is f? F is just x. So this m of x is just the integral from square root of 2 negative 2 these functions there. Okay, and if we compute that quickly, we get, let's see, what is this thing? 4 minus 4x squared plus x. Okay, so what we have here is 4x minus 4/3 x cubed plus 4/5 x sorry, from okay, and it is twice of this formula using symmetry. There. Okay, so you plugged in a square root of 2, so 4 square root of 2, 4/3 2 to the 3/2 plus 5/2. This is square root of, sorry, 2 to the 8 square root of 8. This is square root of 32. Yeah, you can simplify this one. All right, so, and the mass is, well, compute directly the integral. Density times area. Area is just x. Okay, so that's from U symmetry, then Y symmetry. All right, so if you plug that in, 2 delta 2x minus 1/3 x with a bounds. Okay, so that's how we can do that. Okay, so in the end, it's just sorry, what is, yeah, mx divided by m. So you get the number. Well, since you can use your calculator, Maple or Wolfram Alpha, you can compute this one. Questions? Okay, so far? Right. So you don't need to memorize the formula, but you derive the formula based on the picture. Okay. All right. So let's keep the a volume of a donut. Donut, technically, donut is torus. The shape here. Okay. All right, this is a shape that you haven't found yet the formula when you're in high school, right? So we really need calculus to compute this one. Just as a recall from the what we have so far is this one here. As a solid of revolutions. Okay, so what we have is this one here. Say, okay, so let's say this is a donut. What you have is this one put at the center of the coordinate. So we say that the important thing is that this radius here, the center, and this one here. Okay, so if you make a cut, it looks like a, say, a circle here. Okay. So say a circle of radius, so this is 2, say 1, 2, 3. Okay, so take a circle, say half circle, and say you rotate this one, and you get half a donut. All right. So this function is all right. So you translate x 2 to the right and keep the y. So this is radius 1. So that's the equations. Okay. So one thing is that this is if you uh, take the sample, revolve this, and you get a something that looks like this one. Is and you cut this up, and you get a rectangle with some very thin width. Okay, and so this is the x. So this length is just 2 pi x, circumference of this circle. Okay, and the height is just this is y. The height. Okay, thickness. Thickness is this one, delta x. Okay, so this volume is 2 pi xi, right, times y times delta x. And what about y? So we need y here. So if you have, so y is, well, this one minus the square root. Okay, so this is 2 pi x square root of x. Okay, so then it's now easy to find the formula for so v is the sum. Oh, sorry, it's not dx but delta x. So then now we compute. V is just 2 pi integral x from 1 to 3. Right, so that's the volume of the donut here. Okay, so that's a big donut because the outer radius is 3, the inner radius is 1. Let's see. Well, that's a typical donut anyway. Get the Dunkins. And so this is the formula. Integral, you can compute the integral. The thing, what I meant is you can use the calculator to compute this integral because this is not something that has the antiderivative. You gotta use some tricks to do this. We'll do this later. The trigonometric substitutions. Okay, so this is a substitutions to compute. So that's not an easy one. All right, but use maple or program. Okay, or if you want to compute that, well, Let's do this one. X times square root of 1 minus. Okay. Let's do this one because I have maple already here. Okay, so let's do this one. A integrate, I should say, uh, integrate all right, so what is that thing? X times times uh, tab square root of 1 minus x minus 2. Is that right? Yeah. Square root times, yeah, okay. But they say that x from 1 to 3. Let's hey, just give you. Is that correct? Yeah. P. Okay. So what we have is 2 pi times this one. All right, so let's this turns out to be 1 pi. So in the end, we have 2. Okay, so that's the volume of the donut. Uh, we'll compute this using a center of mass, much easier. Okay, so let's take a break for 5 minutes.